Okay, in the last lecture we are discussing about the Verilog code for D flip flop, and then we derived the T flip flop using D flip flop, and we have instantiated this D flip flop code to write the code of T flip flop. Now, the further extension is using T flip flop we can construct ripple counter. If I consider 4-bit ripple counter, so we know that the counter, so it will start with some state, after some clock cycles it will reach the same state. So, the number of clock cycles required to reach the same initial state is called as the modulus. Okay. So, if I take this 4-bit ripple counter, the modulus of this one is 16. Modulus will be normally 2 raised to the power of n, where n is the number of bits in the counter. So, here n is 4, this is equal to 16, where n is equal to 4. Means the counter will goes through the states. You can write the starting state is 0 0 0 0, then it will goes to 0 0 0 1, 0 0 1 0, 0 0 1 1, 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1, 1 0 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, 1 1 1 1. After that it will goes to the initial state. Okay. So, this is each state you can represent in the box or a circle. Then this particular diagram is called as a state diagram. This is the state diagram of mod 16 counter. Now, how to realize this? Okay. So, normally this ripple counter is realized using T flip flops. So, each bit we require 1 T flip flops. So, for 4-bit ripple counter we require 4 T flip flops. This I will start with T0, because these outputs will call as Q3, Q2, Q1, Q0. This is MSB, this is LSB. So, the output of this one is Q0. This will require the clock. Now, to apply the external clock. This is T1, Q1. This also requires the clock. The clock of this one is the output of the LSB flip flop. Similarly, the clock of T2 is Q1, clock of T3 is Q2. So, these are the points where we will take the outputs. this is Q3, Q2, Q1, Q0. We will get this sequence. So, here normally in most of the books T0 will be taken here T1, okay, but I am following the same order in which the MSB to LSB is given. Okay. So, depends upon the LSB bit, this bit will affect, this bit will be affected by Q1, this will be affected by Q2 and so on. That is why I am writing in the same order. This is LSB, this is MSB. And here one important thing is each T you have to make as 1. So, we know that for the T flip flop the truth table is T Qn Qn plus 1. If T is 0, whatever the previous state will be retained, this becomes Qn only. If T is 1, if previous state is 0, present state will become 1, previous state is 1, present state becomes 0, this is complement of Qn. Okay. So, what happens is when T is equal to 1, the flip flop toggles. At every clock signal. Here this clock can be either positive edge triggered or negative edge triggered. Here I have not given the bobbles, so that means it positive edge triggered. So, if I take the count sequence of this, okay, if I assume that the initial state is Q3, Q2, Q1, Q0, 0, 0, 0, 0 is the initial state. Before application of the clock signal, this is 0th clock signal. How to establish these initial states? We have discussed using preset and clear signals. So, at first clock signal, what happens? So, this external clock is applied, this is CLK which is applied here. Okay. So, whereas the clock for this T1 is Q0, clock for T2 is Q1 and so on. These are the clocks of this, we can call as clock 3, clock 2, clock 1, of course, this you can call as clock 0. So, this is clock 0 here. So, because clock is 0, so 0 to 1 transition. Okay. So, 0 to 1 transition, if I take this clock signal, this is logic 0 to 1 transition is positive edge. See here I am assuming that these are all positive edges because I have not taken the bubble. So, at positive edge what happens is, so this will changes, Q0 will changes 0 to 1. So, in order to change this Q1, because T1 is always tied to 1, Q1 changes when and only when Q0 changes from 0 to 1. Because positive edge 0 to 1, if it is negative edge 1 to 0. Okay. Let us assume that otherwise the negative edge, for this otherwise you have to change the circuitry from negative edge means 1 to 0. These are all I am calling as negative edges. So, this is one complete clock. So, this Q0 will changes always. At second clock signal this becomes 0, at third clock signal this becomes 1, because this clock, external clock that we are going to apply is, this entire thing is called as clock 1, this clock 1. This entire thing is called as clock 2, this clock 2. So, over this entire thing the negative edge also will comes, positive edge also will comes, but because these are all negative edge triggered, at this particular point this q naught will changes from 0 to 1. Again at this particular point q naught changes from 1 to 0. Again at this particular point q naught will change from 1 to 0 and so on. Whereas the condition for the q1 to change is q naught has to change from 1 to 0. So, here from here to here q naught has changed from 0 to 1. So, it will remains in the same state. Similarly, the condition for the q2 to change is q1 has to change from 1 to 0, okay, because it has not changed, this will remains in the same state. So, condition for the q3 to change is q2 has to change from 1 to 0, okay, but q2 remains in 0. So, q3 will remains at 0 only. So, after the first clock signal the next state is 0 0 0 1. So, at the second clock signal q naught always changes because external clock. If I apply one complete clock signal, it will contains positive edge, negative edge, positive level, negative level. Okay. So, the output will changes. Now, from 1 to 2, so this q naught is changing from 1 to 0. So, q1 also will changes. The condition is 1 to 0. So, the condition is if q naught changes from 1 to 0, q1 changes. So, q1 changes. So, the condition for q2 to change is q1 has to change from 1 to 0, but here it is changing from 0 to 1. So, no change. Here q2 remains at 0, no change. So, as at the third clock signal, this changes from 0 to 1. 0 to 1 transition means no change, 1 to 1 means no change, 0 to 0 means no change. So, fourth clock signal, this always will changes. 1 to 0 means change, 1 to 0. 1 to 0 means there is a change. So, this 0 to 1 means no change at q3. 5, 0, this is 1. So, this is 0 to 1. So, 0 to 1 transition means no change, 0 to 0 means no change, 1 to 1 means no change. Similarly, 6, 1 to 0, 1 to 0 means change, 0 to 1, 0 to 1 means no change, 1 to 1 means no change. 7, this is 0 to 1, so 0 to 1 means no change, 1 to 1 means no change, 1 to 1 means no change. 8 clock signal, this is 0, 1 to 0 means change, 1 to 0 means change, 1 to 0 means change. 0 to 1 no change, 0 to 0 no change, 0 to 0 no change. So, this is 1. 1 to 0 change, 0 to 1 no change, 0 to 0 no change. 0 to 1 no change, 1 to 1 no change, 0 to 0 no change. 1 to 0 change, 1 to 0 change, 0 to 1 no change. 0 to 1 no change, 0 to 0 no change, 1 to 1 no change. 1 to 0 change, 0 to 1 no change, 1 to 1 no change. 0 to 1 no change, 1 to 1 no change, 1 to 1 no change. At 16th clock signal, this is 1 to 0. So, 1 to 0 means change, 1 to 0 means change, 1 to 0 means change. This is your initial state. So, 16 clock signals are required to get the same initial state. So, the modulus is 16. So, this is the 4-bit ripple counter. So, the name ripple counter is because this bit ripples through, this q naught change will reflect in q1, q1 change will reflect in q2, q2 change will reflect in q3. So, this change is in the form of a ripple. So, this is name ripple counter, also this phenomenon is called as asynchronous counter. So, why the name asynchronous is the clock is different for the different flip flops. Okay. So, on the other hand we have the synchronous counters also where the clock is common to all the flip flops, okay. But the complexity of the synchronous counter is more than the complexity of the asynchronous or ripple counters. So, normally in applications where complexity is important, means area and power, we prefer ripple or asynchronous counters. The applications where speed is important, we will prefer synchronous counters. Now, this is our 4-bit ripple counter. What is the Verilog code corresponding to this one? So, we have written here for this T flip flop, we have to instantiate this 4 times. So, this T flip flop name given is TFF. So, we have to call TFF, output is Q, input is T and another input is clock. Overall the module name is 4-bit ripple counter. So, what are the overall inputs and outputs of this ripple counter? Clock is the input, outputs are Q0, Q is output, later we will define as Q0, Q1, Q2, Q3, Q and clock. Output 320 Q. So, this register no need to declare, because here also we are not going to use this register, because we have defined this register in the main module, D flip flop module. So, that will take care about the remaining modules, because we are going to instantiate this input clock. This T we are going to derive from the D, right. So, instant is 4 instances of T flip flop So, the name that we have given for the T flip flop is TFF. I will give some another sub name as TFF0. We have to define this as output, input and clock. Okay. So, inputs we can also define this input here T. We can write input 3:0 T. So, T first one is, so yes, we have to give the first output, then the input, then the clock. So, for T flip flop 0, output is clock is Q0, input is T0, clock is external clock. You can see from this diagram. So, for this output is Q0, input is T0 and clock is external clock. Okay. Whereas, for the next one, input is T1, output is Q1, clock is Q0. T flip flop TFF1, output will be Q1, input will be T1, but in place of clock we have Q0. Similarly, third flip flop TFF2, output is Q2, input is T2, the clock for the second flip flop is Q1. T flip flop TFF3, output is Q3, input is T3, clock is Q2, this Q2 end module. This is how we can construct the higher level modules from the lower level modules by instantiating the lower level modules. Okay. So, see about we have considered about D flip flop, from that we have constructed T flip flop, From that we have constructed a ripple carry counter. We can simply call it ripple counter also, ripple carry counter also. Okay. In the main program of the D flip flop, the operation is very simple. So, we can write the code for the D flip flop, just simply assigning D is equal to Q, but this is not the case of a JK flip flop. Okay. In JK flip flop, the output we cannot define, like just simply Q or Q naught or Q naught bar. Okay. So, it has to follow a truth table. So, how to write the Verilog code for the JK flip flop? So, we know that JK flip flop, if I take only this block, because we are not interested in the internal circuit diagram, in case of behavioral modeling, this is JK Q bar, then we have clock, so what is the truth table of this? JK Qn plus 1. If it is 0 0, whatever the previous state will be the present state. Now, this is 0 0 1 1, only previous state is present state. If j is 0, k is 1, regardless of the previous state, output remains in 0. This is independent of this state. Conversely, if j is 1, k is 0, regardless of the previous state, this remains in 1. For j is 1, k is 1, the present state will be complement of the previous state. This is Qn bar. This is for the master slave JK flip flop. Okay. We have already derived this table and we have discussed the internal circuitry of this JK flip flop. Okay. So, now how to write the Verilog code? Module JK flip flop, inputs are JK, output is Q. I will use small letters. Okay. This is output, inputs are J, K, clock. Output. So, also we have to declare as a register. So, two keywords Q, because this is target output. Input J, K, clock. Now, here we cannot write the expression for the output in case of D flip flop like Q is equal to D. Okay. Whereas, in JK flip flop there is no such expression. Okay. So, you have to describe this truth table in the Verilog code. Okay. For that we will use a case statement, always at this, because I have not given the bubble, you can call as positive edge, pos edge of the clock, case. Who is going to decide? J comma K. This you have to put in flower bracket. Case 2 bit 0 0. J is 0, K is 0. What will be output? You have to use the non-blocking statement in case of sequential circuits. Q itself. So, this is present state, this is previous state. To be 0 1, Q is equal to 0, because Q is 0 here. To be 1 0, this is colon not semi, q is equal to 1, 2b 1 1, q is equal to q bar. This is complement operation in end module. This is about the JK flip flop. So, in case if it cannot be expressed as a Boolean expression for the output in terms of inputs, then we have to describe the truth table. Okay. Now, using this JK flip flop, if you want to design any circuits, you can instantiate these JK flip flops. Okay, using now this JK flip flop Verilog code, we can construct a 4-bit or 3-bit synchronous counter. Okay. So, we can instantiate this JK flip flop to design the synchronous counter. Okay. So, till now I have discussed about the ripple counter. So, ripple counter will act as asynchronous counter. Okay. So, which will be having different clocks for the different flip flops. Okay. So, in that way the asynchronous counter is slow, the speed of the asynchronous counter is less. Okay. To improve the speed, we have to use the synchronous counter, where the clock will be common to all the flip flops. Okay. Now, I will discuss a 3-bit synchronous counter using JK flip flops. So, this design of synchronous counter is not as straightforward as asynchronous counters. Here we have to use excitation table to design the synchronous counter. Okay. So, 3-bit synchronous counter, as the name implies, we have total 8 states 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. After that it will come to the initial state. The modulus of this counter is 8. After 8 clock pulses, we will get the initial state. Okay. So, in order to design this, we have to choose the type of flip flop. We can design the synchronous counter using any flip flops. Here I am using JK flip flops because I have written the code for the JK flip flops, so that I can instantiate this JK flip flop code. Okay. So, I am using JK flip flops. The number of bits is equal to number of JK flip flops. We require 3 JK flip flops. You call the names as J3 K3, J2 K2, J2 K2, J1 K1, J0 K0, and the corresponding outputs are Q2 Q2 bar, Q1 Q1 bar, Q0 Q0 bar. So, the design procedure is we have to start with the present state, next state, then flip flop input functions. So, the states are Q2 Q1 Q0. What is the next state? Q2 Q1 Q0. To get this, what are the inputs required? J2 K2, J1 K1, J0 K0. So, this design procedure is exactly similar to the conversion of one flip flop into another flip flop procedure. Okay. So, for 0 0 0 present state, after clock signal 0 0 1 is required. If the present state is 0 0 1 itself, the next state is 0 1 0. So, like that for 0 1 0 0 1 1, 0 1 1 1 0 0, 1 0 0 1 0 1, 1 0 1 1 1 0, 1 1 0 1 1 1, for 1 1 1 0 0 0. Now, how to find out the flip flop input functions? Okay. For that, we have to use the JK flip flop excitation table, which we have already discussed in the earlier lectures. So, Qn Qn plus 1 Jk. What is excitation table? 0 0 0 x, 0 1 1 x, 1 0 x 1 1 1 x 0. So, here Q2 is changing from 0 to 0. So, for 0 to 0 the inputs required are 0 x. Q1 is also changing from 0 to 0 0 x. Q0 is changing from 0 to 1, for 0 to 1 1 x. So, like that in the next row 0 to 0 means 0 x, 0 to 1 means 1 x, 1 to 0 means x 1. So, next row 0 to 0 0 x, 1 to 1 x 0, 0 to 1 1 x. So, 0 to 1 1 x, 1 to 0 1 to 0, 1 to 0s are x 1 x 1, 1 to 1 is 0 x 0, 0 to 0 is 0 x, 0 to 1 is 1 x, 1 to 1 is x 0, 0 to 1 is 1 x, 1 to 0 is x 1, 1 to 1 is x 0, 1 to 1 is x 0, 0 to 1 is 1 x. Similarly, the last one is all 1 to 0s, 1 to 0 is x 1, x 1, x 1. Now, what are the Boolean expressions for j 0, k 0, j 1, k 1, j 2, k 2? We can see that in j 0, k 0 columns, so all the values are either ones or do not cares. So, if all the values are ones or do not care, so do not care can also be taken as 1. So, the values of j 0 is equal to k 0 is equal to permanently 1. And if you solve for this j 1 using k map, j 1 is equal to sigma m. What are the min terms? So, this is one min term, corresponding min term is 1, this is another min term, this is 5, sigma d. What are the do not cares? This is 2, 3, 2, 3, then 6, 7, 2, 3, 6, 7. This is Q2 MSB, Q0 LSB. So, Q2 Q1 Q0 0 0 0 1 1 1 1 0 0 1. So, min terms are 1 0 0 1, 0 0 1 is this min term, 5 is 1 0 1 is this min term, do not cares are 0 1 0 2, 0 1 1 3, 6 is 1 1 0 1 1 1. So, this is one 4 box combination. Therefore, the value of j 1 is equal to simply q 0. Similarly, if you solve for k 1 also you will get q 0, and if you solve for j 2 you will get j 2 is equal to k 2 is equal to q 1 q 0. Okay. You can do in a similar manner. So, what is the complete the design of 3-bit synchronous counter? You have 3 flip flops. This is j 0, k 0, q 0, j 0 is equal to k 0 is equal to 1, we have just derived. This will be having clock. So, an important thing is in case of synchronous counter the clock is common to all the flip flops. That is why the speed of synchronous counter is more when compared with the asynchronous counter. And j 1 k 1 is nothing but q 0, the same q 0 is applied here also. and J2 K2 are J2 K2, this is Q1 Q1 bar is Q1 Q0. So, this Q1 is this, Q0 is this, you have to connect through the AND gate. This output you have to connect to J2 as well as K2. This is the complete circuit diagram of a 3-bit synchronous counter. So, we know that using T flip flop we have derived this 3-bit asynchronous or ripple counter. If I use the JK flip flop only to have the better comparison. So, T flip flop is nothing but J and K will be connected. So, all inputs will be permanently connected to 1. This is also 1, J1 K1 is also 1, J2 K2 is also 1. If we take the T, simply T0, T1, T2, 3 inputs are 1s. The only difference is here the external clock is applied. This Q0 will act as a clock for the second flip flop, Q1 will act as a clock for the next flip flop. So, this is 3-bit synchronous counter, this is 3-bit asynchronous counter. If we take the relative merits and demerits of this one, so the complexity of this system is less, low complex, because we require only 3 flip flops only, no extra additional gate is required. Here we require additional gate of this, okay. But this is slow, this is fast, but more complex than asynchronous. So, in applications where speed is important, we will go for the synchronous counters. In applications where complexity is important, we will go for asynchronous. Okay. By asynchronous counter is just if want this is mod 8 counter 3-bit or mod 8. If you want mod 16 counter, you add one more flip flop here, you connect the Q2 to the clock of that one. But here we require a design procedure, you have to follow the excitation table and then you have to design. Okay. So, it is about 3-bit synchronous asynchronous counter. Now, I can write the Verilog code correspond to this 3-bit synchronous counter by instantiating the code of JK flip flop thrice. So, we have written the JK flip flop with the module we have written as JK flip flop. So, JK underscore flip flop QK, this was the code for the JK flip flop. So, to instantiate this we have to write JK underscore flip flop with QJK clock. This was the name we have used for the JK flip flop. Okay. Now, by instantiating this we have to write the code correspond to 3-bit synchronous counter. So, module synchronous counter. So, the outputs will be, I will write here itself 3 outputs 2:0 Q, I will call as lowercase letter, comma input 2:0 J comma K, another input is clock. This is initialization. Okay. Now, so J0 K0 should be 1. So, I will assign J0 is equal to 1, J1 is equal to 1, sorry, K0 equal to 1, J1 is we have derived as Q0, K1 is also Q0, J2 we have got as Q1 and with Q0, K2 also same thing. Then you have to instant it. So, JK, the name I have given is FF, I will give as circuit 1, C1. So, the format is we have Q, J, K, then clock. So, for the first flip flop, you can call this JK flip flop, we can give as C0 if we call as. What is Q? Is Q0 and the inputs are J0, K0, but what is J0, K0? 1, 1, and then clock. JK flip flop C1. For C1 output is Q1, J1, K1, but what is this J1, K1? Q0 clock. The third flip flop C2, Q2 is the output, J2, K2 are the inputs, but what is J2, K2? Q1, Q0, comma clock. So, this is how you can obtain a synchronous counter by instantiating the Verilog code of JK flip flops. Okay. So, this is for the counters. Counter is actually a simple synchronous circuit. So, how to design a general synchronous circuit which contains, in addition to the inputs and the states, outputs Qs, but also it will be having external outputs also. Okay. So, that design procedure and Verilog code correspond to that one we will discuss in the next lecture. Thank you.